So the lesson we're going to look at with vectors, it's the same section, 8.5, but it is part 3. Remember, this is a different book that we're using this week, so if you look at the PDF file for the homework, it's probably going to say section 5.5 on it, but it is page 352. So if you just go to the lesson for today on Schoology, the correct PDF is in the folder that you need. Okay, let's look at dot product. So as far as doing things with vectors, okay, things that we've done so far, we've taken two vectors and added them together, we've subtracted them, we've scaled them, and we found the length of them. Today, what we're going to do is look at how we can take two vectors like that and find the angle between them. When we talk about the angle between two vectors, we're always talking about the angle that's going the short way between the two. We're not talking about the angle outside there. Okay? It's always the angle that's less than 180. Okay? I guess it could be exactly 180 if you had two vectors like that. That's exactly 180. So that's what we're going to take a look at. And to find the angle between two vectors, you have to know how to find what's called a dot product. So when we multiply vectors together, there are two ways to do it. This is what we're going to look at. That notation right there, that dot, that's the symbol for a dot product. So the question on a test or in the homework is asking you to find a dot product. You're going to see a dot between two bold letters. Now, there's another way to multiply vectors which we are not going to look at, and that's called a cross product. You'd see this symbol. This is something that you can only do in 3D. Okay, cross products don't exist in 2D, and we're still doing 2D, so we can't do cross products yet. If we did one more day on vectors, that would be the day we would get into 3D, and I would show you what a cross product is. But we're going to stick with a dot product. Because there's two different ways you can multiply vectors together, you always have to put a symbol between the letters. You cannot write this. In vectors, that would mean nothing. That's just two vectors next to each other. Normally, when you do multiplication in algebra, yes, you can put two letters next to each other. But those are vectors, and you need to put either a dot or a cross between them. So whoever's looking at it knows which one do you want them to do. I wouldn't know what to do looking at this. All right, so let's look at how we do a dot product. Well, to do a dot product, the first thing is you need to have two vectors. Each vector is going to have its own horizontal component and vertical component. I'm calling the horizontal component of vector v a1. Again, that would be an actual number. And the horizontal component of vector w, a2. The vertical component of vector v, I'm calling b1. And the vertical component for vector w, I'm calling b2. To find the dot product, we're going to do something with those four things. The a1, the a2, the b1, and the b2. Now remember, those would all be numbers. So if I scroll down, I can show you what an actual problem would look like. And then I'll come right back to this. When you do an actual problem, that's what it's going to look like. The A1, the A2, and the B1 and the B2, they're all going to be numbers. So this is how you find the dot product. So first of all, notice on the left-hand side of the formula, I put the notation for a dot product. And you say d dot w. That's how you say it. You don't say d times w. because in vectors, times doesn't mean anything because there's two ways to times, dot and cross. So v dot w, and it's a very, very simple one. You take the two horizontal components and you multiply those two numbers together, just like that. And you're going to add to it the product of the two vertical components, b1 times b2. And that's how you find a dot product. So you multiply the horizontal components together, multiply the verticals together, and then add them up. So let's look at this part right here. A1 times A2. A1 and A2 are numbers. So what would you get if you multiply A1, which is a number, times A2, which is a number? Like in general. Yeah?
A number.
You're going to get a number. So A1 times A2 is going to be a number. How about when you do B1 times B2? What kind of thing are you going to get right there? Yeah? Yeah, you're going to get another number. Could be a different number, could be the same number. But you're going to have a number plus another number. So what does that give you? Yeah?
A number.
A number. So when you find a dot product, the answer that you get is a number. Like 7, 2, 5, -8. It's some number. What that number means, well, I kind of already gave you a hint at what we're going to do. We're going to find an angle between two vectors. And you need that number to do it. Let's try an example. Okay, so here's two vectors. And I want to find the dot product, v dot w. So when I'm doing a dot product, I usually write it out first, everywhere that I'm going to need to put a number. So it's going to be something times something plus something times something. And when we fill in what's the numbers in those parentheses, I want to make sure we follow this exact order. So what would go in my first parenthesis? 2. Okay. And my second parenthesis? Yep. 5. So there's the product of my horizontal components. 2, 5. The reason we did the 2 first and then the 5 is because the V was first and the W was second. Okay. And then how about my third parenthesis? What's going to go in there? Yep. -3. And the last thing I need to fill in? Yep. 3. Okay, so now do that out, and that's going to be your dot product. 2 times 5 is 10. -3 times 3 is -9. And that's going to give me a dot product of how much? Yep. 1. Now that 1 means something. I'm going to tell you what it means later. But that is the dot product between those two vectors. 1. Any question on how we got 1? So now what we're going to do is we're going to look at the dot product, but I want to switch the order. Now I want to do W dot V and see what happens. Okay, and just remember this time, W is first, V is second. So what's going to be in these two parentheses in the correct order if W comes first and V comes second? Yep.
5. 2.
5 and 2.
And then 3. And -3.
And then 3 and -3. So when we do the dot product with W first, what do I get? Oh, quick.
Just one again?
Yeah, we get 1 again. So what does that mean? It doesn't really prove it, but if W dot V came out the same as V dot W, that means something in math. Yep. Well, V and W are not equal. They are different vectors. These numbers would have to be identical if they were equal. But there's a name for when you can switch the order. When you multiply it, you get the same answer. Yeah?
Isn't that one of the properties, like is it the community property?
Commutative.
Commutative.
So vector multiplication, at least with a dot product, is commutative. The cross product, if we were going to learn that one, is not. And that would probably be one of the first times you've ever seen multiplication in math where you switch the order and you get a different answer. Usually multiplication, you can switch the order and it doesn't make a difference. But with cross product, it does. But dot product, it does not. All right. Now let's try V dot V. So we're dotting V with itself. Okay, so you don't need W at all for this one. So what am I going to write down to do the calculation for the dot product with V dot V? Yeah?
Would it be like 2
2 times
times 2
2
plus -3?
plus, what did you say?
-3 times -3.
Yep, -3 times -3. So that's going to give me, before we figure that out actually, I want to think about this a little differently. What's another way to write 2 times 2? I don't mean the answer to 2 times 2. I mean a different way to write that, yeah?
2 squared.
2 squared plus, how about a different way to write -3 times -3? -3 squared. Does that kind of look like something we did earlier in the week? Square the 2, square the -3. It's missing something, but it's almost like something we did earlier in the week. Yeah? It's almost like the Pythagorean theorem. When you dot a vector with itself, you're basically doing the Pythagorean theorem, except there's one thing missing here. What's missing that we're not doing? Yeah? Yeah, you're not taking the square root of it. And when we use the Pythagorean theorem, what did that help us to figure out about a vector? We use the Pythagorean theorem to find the magnitude. So dotting a vector with itself is almost like finding the magnitude, except you don't take the square root. If I took the square root of that number, that would tell me the magnitude of vector v. It would be the square root of 13. Because I squared the first number, I squared the second number, I added them together. All that's left would be to take the square root if you wanted the magnitude. This question wasn't about the magnitude. But that's the dot product, 13. All right. How about W dot W? What would be my calculation for W dot W? Yep. What?
5 times 5. Or no, wait. Yeah. Wait, what was the question?
W dot W.
W dot W. So yeah, it would be 5 times 5 and 3 times 3.
And what do you do with those two things?
Do that together.
Yeah. So it's square the 5, square the 3, add them together, and stop. If you did one more step and took the square root, you'd be finding the magnitude of W. Right? So I'm just trying to get you to see the connection between dotting a vector with itself and finding the magnitude. They're almost the same thing. Just one has a square root and one doesn't. So square the 5, square the 3. So that's 25 plus 9, which gives me 34. So now that you know w dot w, what if I asked you for the magnitude of w? What would that be? Yeah?
You just get a square root of and start
Which would be
square or root of 34.
square root 34. So dotting a vector with itself gave us 34. The magnitude of the vector would be the square root of 34.
Would we have a square root like that if it were to be like square root of 34 where it doesn't come out with like a number with no decimal? Would you just leave it at square root of 34 or would you solve it all the way?
If the question sets around to 2 decimal places, then you'd want to do it out. If it doesn't, you can leave it as a square root, always reducing it as much as you can. There is no perfect square that goes into that. 4 times 9 is 36, and 16 times 16 is 32, so that can't be reduced. Okay, do that. Alright, let's try this one. So, written a little bit differently, it's not with the I and J notation, it's just the other notation. The vector 2, 6, dotted with the vector 0, 0. Okay. What do I get when I find the dot product between those two vectors? Yeah,
0.
0. Can you be more specific about what kind of 0? Like 0. What is 0 in this case? Like, is it a measure of like angle? Is it temperature? Can you be more specific about what 0 is?
No, it's just a number.
It's a number, exactly. The answer here is a number. So the answer is 0, the number. Compared to this, what's that? Yep,
Is that a vector?
that's 0, the vector. That's what this is. That's the 0 vector. What I just circled, that's not a number. It's the 0 vector, which can be written with this symbol. So just make sure when you write the answer to a dot product, it's always a number, okay? Not a vector. Any questions why we got the 0, the number 0 there? So we know that certain properties work with multiplication, like commutative property. You just saw that that one works with vectors. But you can't assume that any properties you know about numbers apply to vectors. You can't assume that that does work. But distributive property does carry over. So if you understand like what the distributive property is with numbers, you can do distributive property with vectors, at least with a dot product. So if you had 2 vectors to add up and then find a dot product, you can do it 2 different ways. You can add the vectors together first, get the answer, and then find the dot product. Or find the dot product with the first one, find the dot product with the second one, and then add those 2 results together at the end. It works both ways. So at least for dot product, we know distributive property works and the commutative property works. Those are really the only 2 that we're going to talk about. Yeah.
So, was that u times v plus u times w, or was that u dot v?
These are all dot products.
Okay.
U dot. There's no such thing as u times v when we're talking about vectors. These are all vectors, so they all should look bold. You just stop tracing over them. Alright, so now let's think about how we could find an angle between two vectors. Let me get a grid. Let's use. Yeah, let's use it. Alright, so I'm going to draw two vectors in quadrant 1 and see if we could figure out the angle between them. Let's draw that vector like that. And then let's draw one. This one. Like that. Well, I don't want it to come out to 90, so I want to do something different than that. Let's do it like that. I don't think that's 90. Okay, so there are two vectors, and the goal is to figure out that. Okay. Anyone have an idea how I could figure that out with what we already know about trig before I show you anything I'm going to show you? Yeah?
You get into a triangle.
Okay. How would you make that into a triangle?
You would connect, or just, not connect, but like draw a connection between the two ends of the vector.
All right, so we can connect that. Now we've got a triangle. And if we really wanted to, what could we figure out about that triangle? It's something that we're not given, but we could find it several times pretty easy, yeah.
We can find both of the bases.
We say that?
We can find like 2 legs.
Yeah, we could find 2 legs. We could find all 3. Right? We could find how long each of those legs are. One way that might make this a little easier, I'm not sure if this is going to work. I'm going to try it. Is I'm going to group all that together. I'm going to rotate it. Still the same answer if I rotate it. But what I'm trying to do is get one of the sides to line up nice so I could count it, but then the other side doesn't line up nice. So that wasn't a great idea because it ends up in the middle. I'll just leave it like that. Okay. So let's start with this. Actually, let's look at all 3 of these sides. How are you going to find the length of each one of those sides? Yeah?
You could like turn them into triangles themselves.
Yeah, we're just going to make basically triangles out of all of them. Now we know this side is 3. This side is 1. Which means that that side would be the square root of how much? 10. So there's that side. Okay, now we could use a different color. Let's do this one. This side is 2. That side is 2. So what's the length of that side? The square root of 8. Is 2 times 2 8? No. So let's just leave it as square root of 8. So square root of 8. Let's do it one more time. So this side is 1, 2, 3, 4, 5. And this side is 1. So how long is that top side? Square root of, 26. So now you have a triangle where you know side, side, side. You know all 3 sides. We've talked about it before. There's a law you can use to find a measure of an angle if you know all 3 sides. Does anybody remember what law There were two of them we studied this week. Law of this and law of that. This is law of that. Yes. This is law of cosines. So law of cosines looks something like this, if you remember. Starts out like the Pythagorean theorem. One side squared equals the sum of the other two minus twice the other two times the cosine of the angle across from the letter you started with. So let's fill in our numbers, they're all square roots, into that formula and see if we can get the angle. Right? So if you want to look at like what the letters are going to be, this is going to be like our A, that's our B, and that's our C. So C squared, actually when we square them, it's going to work out nice. What's C squared? Yeah, 26. What's A squared? Yeah, 8. And B squared? Yeah, 10. Minus, I need my calculator, 2 times A times B. So 2 times the square root of 8 times the square root of 10. Okay, so we're going to get about 17.89. Minus 2AB times the cosine. Well, that's what I don't know. Gamma is my question mark. Okay. What can I do next on the right-hand side just to simplify it a little bit?
Combine like terms.
Yeah, we can combine like terms. So that's 18 minus 17 cosine gamma. Now I need to move something to the other side. What has to go over to the left? Yeah?
18 minus 17.89.
Uh,
Or just 18?
Just 18, right? So we'll subtract 18 from both sides. That's gone. And 26 minus 18 gives me 8. Okay. Now we've got to get the negative 17 on the other side. So how would we move that over? Yeah.
Divide each side by negative 17.89.
Yep. So 8 divided by negative 17.89 equals that. And now I need to get rid of my cosine. Which, yep.
You have to take the, what is it, arc cosine?
Arc cosine or inverse cosine. That, if I did everything right, should be the angle between the two vectors. Now, I told you we were going to use the dot product to find the angle. Did I use the dot product in any of that? No. So then there has to be an easier way to find the angle than going through all this. Not that this doesn't work, it does. Let's write down what we just got. 8 divided by negative 17.89. So the angle, I'm estimating it's about 116.56. Right here. That looks right. It's a little bit, looks like it's a little bit more than 90. So I'm just going to write that down, and we'll come back to that number in a second. So the point here is you can find the angle between two vectors right now without me teaching you anything else. It's not the most efficient way to do it, but you can do it. So what's a more efficient way to do it? Well, what law did we just use? We used law of cosines. Well, we're not going to be able to get away from cosine. Cosine is still going to be part of this formula, but it's going to be a little bit more compressed. It's going to be a shorter formula than what we just went through. This formula is basically doing the law of cosines for you to find the angle between two vectors. You need to find three things. You need to find the dot product between your two vectors. You need to find the length of your first vector and the length of your second vector. And once you know those three things, Put them in the formula. And you're going to end up doing inverse cosine, just like we did before. So let's try the problem we just did with this formula. So you probably already know this, but these two double bars, again, that symbol means magnitude. So the denominator is the length of u times the length of v. Let's try that one. Okay, so to use that formula, we don't have to worry about this third side. The only thing we have to focus on is the first vector that I was given and the second vector that I was given. So just focused on those two bold vectors in black. All right. Let's start by finding the dot product between those two vectors. All right, so I need to write down what these vectors are. This one is 1, 2, 3i plus 1j. So it's 3, 1. So we'll call that vector u. 3i plus j. Let's call the other bold vector v. That's negative 2i plus 2j. So negative 2i plus 2j. Any questions on how I figured out the components for those vectors? It's basically these triangles that I just drew. But don't worry about this top one. You just need the ones that are bold. All right, let's do the dot product. U dot V. What are the first two things I multiplied together to do the dot product? Yep.
3 and negative 2.
3 and negative 2. And the next two?
1 and 2.
1 and 2. So that's going to give me a dot product of how much? Yep. Negative 4. There's the first thing I need, the dot product. The next two things I need, I already have. What's the length of u is 3, 1. What's the length of that vector that I labeled with the red triangle? Yep. Square root of 10. We already know that from the Pythagorean theorem. And the magnitude of v, what was the length of the vector that I labeled with the green triangle? Yep. Square root of 8. That's everything we need to find the angle between the vectors. So let's plug them into the formula and see what happens. Cosine of our angle equals the dot product, which is negative 4, divided by the product of the magnitudes. Square root of 10 times the square root of 8. I probably would have just put those together and said square root of 80. You can do that. But that's okay. So what's my last step that I have to do on each side to get rid of cosine? Yeah?
Take the inverse cosine.
Yep. So it's going to be the inverse cosine of negative 4 over square root of 80. And the hope is when I do that, I get 116.5 roughly. Rounding, it might come off a little bit. Let's see. So this is not using law of cosines at all. It's using the dot product. Inverse cosine of negative 4 divided by square root of 80. And we get 116.56. We get exactly the same answer. So when we're finding the angle between two vectors, Most people prefer to use this formula because it's a lot shorter than the law of cosines. And that's how we'll do it. Any questions on how I did it this way? What we're not going to go through is why. Why does this work? Why did it give us the same answer as law of cosines? We're not going to go through that. All right, I think I've got, let's see. Well, I had another one. Does anybody want to see another one where you find the angle between two vectors? It's like the one we just did. Okay, so let's do it quick. Three things we need: dot product, length, length. Okay. First two things I'm going to multiply for my dot product are what?
4 and 2.
4 and 2. So we got 4 times 2. And say on the next two things I'm going to multiply together for my dot product. Negative 3 and 5. So that's actually going to give me 8 minus 15, which gives me how much? Negative 7. Okay, so there's my dot product. Now we need the length of u. Square this, add them up and take the square root. It's like we're making our triangle. So 16 plus 9. Which gives me a length of what for you? 5. Usually does not come out to a nice number like that. Let's find b. So when we square this, we're going to get how much? 4. You square that.
25.
So 4 plus 25. Okay, so there's the three things that we need. What goes on the left side of the formula that I just gave you to find the angle? Yep. Cosine of the angle equals dot product goes in the top, product of the magnitudes goes in the bottom. And how do I get rid of the cosine? Yep. Inverse cosine. Just be careful if you want to type it all in at once. Use parentheses just like this. So negative 7 divided by, and I put the denominator in parentheses because I wanted to multiply 5 times the square root of 29 first. If you don't, I think it's going to mess up. And that's your angle. 105.07. Questions on it? Now the last two problems we did, there's nothing special about this angle. 105.07 and whatever the other one was, 116.56. Those are just random numbers. But there is a special case that can happen. Anybody think of an angle that two vectors could meet at that wouldn't be random? The angle would be something special if this happened. Yep. 90. Yep. That's a special one. So if two vectors meet at a 90-degree angle, they are perpendicular. And the word they use when they describe vectors being perpendicular is orthogonal. We know why they have a different word. Sure, there's a reason. But if two vectors are perpendicular, it means they are orthogonal. You might also see this symbol Like in geometry, an upside down T, that means perpendicular. So I'm not really picky whether you say perpendicular or orthogonal or use that symbol. That's all. Okay, so let's think about that for a second. If two vectors are perpendicular, what did you just say that means the angle would be? Yeah? 90. So let's work backwards and see what that would mean. Two vectors are perpendicular. You would know that the left-hand side of your formula already has a 90-degree angle, okay? Because the angle is 90. And then on the other side, you would have a fraction. What fraction would you have? You would have this fraction. You'd have some number in the top and some number in the bottom. I don't know what those numbers are, but I do know the angle would be 90. Well, let's take the cosine of 90 and see what happens on the left. Cosine of 90 is 0. So if two vectors are perpendicular, it means in your formula, the left-hand side is going to come out to 0. Now you have a fraction equal to 0. What's the only way that a fraction can equal 0? There's only one way you ever can divide two numbers and get 0 as the answer. Yeah? 0 has to be in the top. That is the only way you can divide two numbers and ever have it come out to 0. So this must be 0. Well, think back to the formula I just gave you. What's right there in your formula? Yeah? The dot product. Exactly. So if we go back and look at the formula, if what's in the top comes out to 0, that's enough information to tell you your vectors are perpendicular. So all you have to do to determine if they meet at a 90-degree angle is find the dot product, and if the dot product comes out to 0, you're done. They are perpendicular. So if two vectors are perpendicular, the dot product is 0. So it's a very quick way to figure out if they're perpendicular. You don't have to go any further. Dot product is 0, you're done. They're 90-degree angle.
And the only time two angles to be perpendicular is at 90-degree angles.
Yes, perpendicular means it has to be 90.
Yeah, so that's okay. If you, yeah.
It has to be like this. The vectors can be rotated different ways. You know, they could look like that. That's still 90. It just turned. So these can face any way you want, as long as that stays 90. Okay. So let's see if these two vectors are perpendicular. So remember, all you need is the dot product. What am I going to multiply here to get my dot product? Exactly.
2 times 1 and 1 times
2 times 1. And what else?
1 times 2.
1 times 2. What's the dot product between those two vectors? Yeah? 4. Are they perpendicular? No. To be perpendicular, it has to come out to 0. So the answer to this question, are these vectors perpendicular? No. All right, so then what could you change in V or W to make them perpendicular? You can only change one thing. You can't change more than one. Just tell me one thing you could change. Yep.
In either of them, you could make it minus instead of plus.
Right. Make any one of these components a negative, like negative 2 times 1. Now you have negative 2. 1 times 2 is positive 2. now would come out to 0. So make any component negative and they would be perpendicular. So any questions on how you can figure out if vectors are perpendicular? Okay, there's one other, this is the last thing, one other special case that can happen. It's an angle between the vectors, but it's not perpendicular. Anybody think of something else that might happen that would be special? Yeah? Parallel. And there's two ways vectors can be parallel. Those vectors are parallel, and those vectors are parallel. Those are two different cases. Now, I can kind of help you because I want to get an idea of what the angle would be. Imagine you took that vector and you put it right there. What would the angle between those two vectors be? Yeah?
0.
Yes. So if the angle comes out to 0 degrees, that is considered parallel. It's like they're pointing the same way. Now, this one, you could think of more like this. Just kind of moving it to give you like a hint. What do you think the angle would be between those two vectors? Yeah?
180.
180. So let's see if there's a shortcut if we can figure out if the angle is 0 or 180 quickly. Like as quickly as we could do perpendicular. Let's try. So if the angle is 0, we know that they are parallel. They're pointing the same way. That means you'd have 0 degrees on the left-hand side of your formula. On the right, you'd have a dot product in the top and a product of magnitudes in the bottom. I don't know what these numbers would be. But if it is parallel, I know the angle is 0. Well, let's take the cosine of 0 and see what happens. We get 1. We have a fraction equal to 1. How can a fraction, remember dot product would be in the top, product of the magnitude would be in the bottom. How can a fraction equal 1? Yeah?
The top and the bottom would have to be the same.
Right, the top and the problem here is the top and the bottom would have to be the same. That means you need to know the top and the bottom. So you need to know both. You can't just say the dot product and do the quick shortcut like we did the first time. So you would need to know the top and the bottom. So if they come out the same, they are parallel. Well, let's see what happens with the 180. If they're pointing in opposite directions, they would be 180 degree angle. And we would have 180 degrees on the left-hand side. Let's see what happens if we take the cosine of 180. We get negative 1. So the other situation for parallel, you're going to end up with a fraction that equals negative 1. How can a fraction come out to negative 1? Yeah?
The top and bottom are the same except one of them's negative.
Yeah, so again, the problem here is what he said, the top and the bottom are the same, except one of them is negative. So you do need to know the top and the bottom. So there is no quick shortcut for parallel. Either these come out the same, or they come out opposites. But you do need to find them both, or you don't know if they're both the same. So let's try one with parallel. And that'll be it. I already said that to you. If two vectors are parallel, the angle is either 0 or 180. And here's an example. Yeah.
Did you find the slope of both vectors? If it was the same, would you then know that they're parallel?
Yeah, we could also kind of think of it about as slope. Yes. You could think of it as slope if you remember the slope formula. Yep. Most problems I give you, though, it's going to be like in the homework, it's going to be a 3-part problem where you have to find the dot product first, then you have to find the magnitudes, then you have to find the angle. So you're going to have to find the dot product for all of them anyway. But if the question did not ask you to find the dot product, then your way would be faster. Yep, very good. Remember these two vertical lines from geometry mean parallel. Okay. The first two things I'm going to multiply together to get my dot product.
Yeah. 4 and 20.
4 and 20. Okay, next two.
-5, -25.
So -5, -25. So what's that going to give me? 80 and 125. Okay, so what's my dot product? $205. Well, there's one thing I can say right away. What do I know about these vectors right now because the dot product came out to 205? Yep,
Not perpendicular.
they're not perpendicular. Are they parallel? Well, I don't know, but they're not perpendicular. All right, magnitude of V. Magnitude of W. Okay, so magnitude of V. 4 squared gives me 5, -5 squared. So 16 plus 25. Okay. That has a length of square root 41. 20 squared. 400. 25 squared. Yep. 625. So that has a length of 1025. Let's fill all those numbers into the formula and see what we get. Okay, so cosine of my angle equals what's going to go on top? Yep. 205. And what's going to go on the bottom?
Square root of 41 plus the square root of 125 times.
Now, if these are going to be parallel, what am I hoping the bottom is going to come out to here? Yeah?
205.
It's got to come up to 205. You might think, well, yeah, but couldn't it come out to -205? Well, no, because that's a positive times a positive. So it's going to be positive. So if these are parallel, the bottom needs to come out to 205. So, let's see. Square root 41 times square root of 1025 gives me 205. So if you forget that that means parallel, well, you can keep going. And now you have cosine theta equals 1. And now if you take the inverse cosine of each side, the inverse cosine of 1 gives you a 0-degree angle. And we just said if the angle is 0 degrees, they're parallel. So writing 0 degrees here does not answer the question. The question was, are they parallel? So we would write yes. Yeah, don't put 0 degrees. So determine if they're parallel. Yes, they are parallel. Any questions on that? I'll pause the video. I'll get this up before you guys leave. And I'll put the list of test topics in it. The homework is 7 to 17 odd. Each question has 3 parts. The 3 parts are find the dot product, find the angle, and then say whether that means parallel, perpendicular, or neither. Neither means it's not 0, 90, or 180. Okay, so let me pause it and now I'll put the test topics up.